Okay, today we're going to be going over example 7 of your L'Hopital's worksheet. Okay, and so these examples of L'Hopital's, basically we need to use logs to get the right form we want to be able to use it. So let's start with number 1, right? So let's try plugging in infinity to this limit, right? You get 1 plus 2 to the infinity, right? Plug in infinity for x to infinity, right? 2 over infinity is 0, and so you get 1 to the infinity power, which you might think that that's just 1, but actually it's indeterminate. And so but it's not in a form that we can use for L'Hopital's, right? We need something like 0 over 0, or infinity over infinity, or negative infinity over infinity. Those are the 3 forms. So we have an indeterminate form, but how can we get this in terms of that we can use for L'Hopital's? Well, we can take the log of both sides. So right now we have f of x equal to limit as x goes to infinity of 1 plus 2 to the x over x. Well, we can get rid of this exponent by taking the log of both sides. So do ln of f of x we get limit as x goes to infinity of ln 1 plus 2 over x to the x. But we can bring this down because of the rules of logs, or natural logs in this case. And we can bring this x out of the exponent. We get x ln of 1 plus 2 over x. Okay, so you might be thinking, wait a second, we don't really have it in the right form yet for L'Hopital's because we need a denominator, right? Well, that's when we can put the x in the denominator. So if we have an x in the numerator, we can place a 1 over x in the denominator. So this x comes down and becomes a 1 over x. Okay. Just going to put this over here for right now. So if we plug in infinity for these values, we have to make sure we can even use L'Hopital's. We might not even need to, who knows? Find out next time. We plug in infinity for this equation. Remember, when it comes to L'Hopital's, you only use it if you need to, right? In this case, you get ln, the 2 over infinity is just 0, so we get ln of 1 and then we get 1 over infinity is 0. Well, ln of 1 is 0. So in this case, we get 0 over 0, and we do get a form that we need to use L'Hopital's for. Okay? So we need to differentiate both the numerator and the denominator, right? This is where L'Hopital's comes in. If you get a form of either 0, 0, infinity over infinity, or negative infinity over infinity, then you have to, under L'Hopital's, where's the problem? Okay, still x infinity. You have to differentiate both the numerator and the denominator separately. So you're not taking the differential of the entire equation, you're taking the differential of each of the numerator and of the numerator and the denominator separately. So remember, we have ln of 1 plus 2x and we have 1 over x. Okay, and then this is equal to limit as x goes to infinity. And you differentiate this, the differential of ln is going to be 1 over what's in the inside, 1 plus 2 over x. And then chain rule, right? So differential of what's inside, differential of 1, 0, and then differential of this. Well, this is 2 times x to negative 1. So we're going to get multiplied by negative 2, right? Because this is x to negative 1, so the negative comes out, and multiplied by the 2. So negative 2, 1 over x squared, right? And then down here, this is also 1 over x, and we get negative 1 over x squared. You could write this as negative 1 x to negative 2, or you can write it as negative 1 over 1, or negative 1 over x squared. Either way works. But in any case, the x squareds cancel out. The negatives cancel out. We're just left with a positive 1 below. Get limit x goes to infinity. I probably should silence my phone before I start recording, huh? Of oops, 2, the 2's still there, 1 plus, so 2 over 1 plus 2x is what we're left with. Okay, so at this point, we can now plug infinity in, and we get, remember, this is still ln. Remember, we ln this equation, so that's going to be important. This is still ln of f of x is equal to 2 over 1 plus 2 over infinity. Okay, this is a 0. 2 over infinity is 0. Anything over infinity is 0. And you get 2 over 1 or 2, which is equal to ln of f of x. Well, now we want to figure out just what f of x is, so we get e squared is equal to f of x, right? We take the e of both sides. So actually, the answer is e squared, right? We started this out by ln'ing, natural logging the whole equation, right? Right, we natural log both sides. So now we're just undoing what we did by putting each to the e power, right? E to the ln of x just becomes f of x, and e to 2. E of 2, or e to the second power is just e to the second power. So we get limit as x goes to infinity of 1 plus 2 over x to the x power equals e squared. And that's your answer. Okay. Now let's move on to the second question. Okay, so this is going to be the theme. These are all going to be in, these next two are going to be the same thing. They are not going to be in a form where you can, it's not going to be a 0 over 0 or infinity over infinity. It's going to be in a form that's also indeterminate. So you have to use a log to get rid of the exponent, right? If I plug in 0 for this, I get 0 to the 0 power. Indeterminate, but not something I can use L'Hopital's for. So I ln f of x which is, right, because f of x is this, in this case. And so limit as x goes to 0 and we get ln of x to the x power I'm sorry, my writing's not the cleanest. And of course, that allows us to bring the x down. And again, if you plug in 0 here, you get 0 times ln of 0 is negative infinity. So you get 0 times negative infinity. So wait, okay, it's not even in a form of L'Hopital's yet. So we have to, again, drop down the x into the denominator, right? If you know you need to use L'Hopital's, then you know that you need something in the denominator. And so that can be a hint to help you solve some of these problems. And so we get ln of x over 1 over x, right? We're bringing this x from the numerator to the denominator. So x in the numerator is equal to 1 over x in the denominator. Okay. And now when let's make sure that we need to use L'Hopital's, right? We plug that in. We get ln of 0 over 1 over 0, right? And we get negative infinity. 1 over 0 is infinity. So we do know, okay, we get negative infinity over infinity. We do know that we need to use L'Hopital's. So going back to the original, or not quite the original, we need to differentiate both the numerator and the denominator separately. I'm just going to draw this a little bit better. So what's the numerator here? Well, this is ln of x. The denominator here is 1 over x. And from here, this differentiation isn't too difficult. Derivative of ln of x is just 1 over x. And then from here, derivation of 1 over x is negative 1 over x squared. And from here you get negative x squared over x. And so again, you took the natural log of the whole function. These cancel out. You're left with a negative x. Just making sure I did everything right in my notes so far. Okay, when you plug in 0, you just end up getting 0, right? It's just a negative x, so plugging in 0, you get 0. Now, this is equal to ln f of x. So we have to e both sides. So we get f of x is equal to e to the 0. And that is equal to 1. Anything to the 0th power, almost anything to the 0th power is 1. And so this means that the answer is, we go back to the original problem. Right, the original problem asks us limit as x goes to 0 from the positive side, from the right side, of fx to the x power, and we determined that this is the answer. It's equal to 1. Okay, so that's number 2 down. As you can see, number 3 is almost the same thing. Instead of x to the x, it's x to the 1x, and instead of going to 0, it's going to infinity. So we're going to follow pretty much the same process. Break it down into steps. Now that we've done it a few times, for these ones, plug in limit. If 0 over 0, or I'm not sure how to write this. I'm going to just call this plus minus infinity over infinity. Use L'Hopital's. Okay. From there, you can plug in your limit again, right? And if it's still 0 over 0 or plus minus infinity over infinity, you can use L'Hopital's again until you don't get an answer in that form. If not, use algebra to get formula into form where limit is 0 over 0 or plus minus infinity over infinity, right? And then you can use L'Hopital's. Now, in this case, we're using logarithms to get the x out of the exponent, or the 1 over x out of the exponent. So in this case, we are using logarithms, but you might have to use other tricks to be able to do that. It's not always going to be logarithms. In these examples, it is. And then from there, use L'Hopital's. Okay. So now I'm just going to go over this last example. Going to clear. Okay. So we put in infinity. We do step 1. We get infinity to the 1 over infinity power. And so that is infinity over 0, infinity to the 0 power, which is not a form we can use L'Hopital's. So we need to get it into 1. Again, we have an exponent here. So we're going to have to use natural logarithms, right? So this is f of x. So ln of f of x and you get limit. Luckily, you can just take the limit outside the natural logarithm. Wow, that's the worst infinity ever drawn. I try and, my writing isn't the cleanest, but I try and make it somewhat legible. Okay, and so ln of x, and we can bring out the 1 over x, right? So at this point, we actually just get limit as x over infinity, x goes to infinity, of ln of x over x. Okay, as you plug in infinity, well, you get infinity over infinity. Ln of infinity is infinity, and x, you plug in infinity for x, you just get infinity. So now we can use L'Hopital's. We got in the form we wanted, right? So again, x goes to infinity. As we need to differentiate both the numerator and the denominator separately. Again, do not differentiate both top and bottom together. Okay, we have to, so ln of x here, and we have x down here, right? If you were to differentiate both together, well, you'd have to use, chain rule, you'd have to, well, in this case, you have to use quotient rule, but we're not doing that. We're differentiating the numerator and denominator separately, which makes it a lot easier for us, actually. Okay, and so you take the derivative of ln of x, you get 1 over x. Derivative of x is just a clean 1. So we just get the limit as x goes to infinity of 1 over x. And when you put that in, you just get 1 over infinity, which is equal to 0. But it is equal to ln of f of x. Remember this. If you're taking the natural log of both sides, you're going to have to eventually put everything to the e power again. Right? So when you e both sides, you get f of x is equal e to the 0, which is equal to 1, right? And 1 is equal to the very original problem. I managed to get through this recording okay, and somehow something's going to mess up at the very last second. Okay, and so this is your answer. So these are all three of problems under example 7 where we have to use logs to make it into a form that we can use for L'Hopital's. So I'm going to clear this, stop annotating, stop share, and that's the end. And let me know in the YouTube comments if you have any questions.